It's my pleasure to introduce Dave Collins. He's a carbon-based life form from Melbourne. He's been programming for 25 years, 25, 15, 25 years, but it took 10 years to work out how to get paid for it. He writes code on Linux, mostly somewhat in Python. He tries to not control the weather, forecast the weather at BOM, and he thinks digital watches are a neat idea. Please welcome him.
So time is an illusion. I'm going to be arguing for the affirmative in this particular discussion. I'm going to start, though. I'd like to acknowledge the traditional owners of this land, the Wurundjeri people of the Kulin Nation, and pay respects to their elders, both past and present. I'd also like to pay my respects to the Wadawurrung people, also of the Kulin Nation, and pay respects to their elders, past and present. And the Wadawurrung people are, for anybody who knows the geography, basically the Werribee River, all the way down to Bellarine Peninsula, off to Lorne and up to Ballarat. And the reason I'm going to talk about them become evident in a second. So today, I kind of could have fitted a million things into this talk. I gave a bit of this talk previously at my work, and I had a lot more history and some more technical stuff in it. I've taken some of that out. I've just got one bit of history, and then I'll get on to more kind of a little bit more Python-related things. I think this talk might end up being re-given in the future as 10 different talks, but who knows, because there's too much stuff in the world to talk about. So my one bit of history is the Wurrung-Yurang, and this is on Wadawurrung territory, down about halfway between here and Geelong. And it's actually a 10,000-year-old sundial/calendar. It's older than Stonehenge, and it's there's some better diagrams of what it does diagrammatically, but that's a good picture of what it is. But it basically is there to tell the transitions from the astronomical seasons. And so the Wadawurrung people would use this, and also the eel traps and various other things in the area as part of their traditional agricultural system. And when you are running essentially an agricultural system, the time of the season and your accuracy about telling seasons is all you need. Leap forward thousands of years very quickly. What about now? Well, now we actually do still keep track of time with respect to the sun, but we do it in a very technical way now. Solar time is still measured. It's measured by a thing called UT1. It's kind of a bit like the old GMT in the sense that it's the time when the sun is kind of directly ahead of Greenwich. Except we actually use it based on some very distant celestial objects, and we measure it with radio telescopes, and we keep track of it, and then various teams of scientists around the world send files back and forward between each other and carefully define what UT1 is. So UT1 is out there. That's the first important part of understanding modern time. Now, wait a second. In 1954, we redefined the second. The second is now 9,192,631,707 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of a cesium-133 atom. The best thing I love about this particular definition was when I went and actually looked it up, I discovered there's a modern revision of it. And I kind of went, what? Like, how can you change things? But they forgot to put stuff in the standard when they made it up that said you had to be at sea level and you actually had to do it at a particular temperature. So nobody wasn't at sea level and wasn't doing it at that temperature, but now the definition is even longer and more clear and more precise about what a second is. So we set atomic clocks, and they've been keeping time since 1954, and that's called International Atomic Time, TIA, from the French name Temps Atomic. Sorry, Dad, I've stuffed up my French. Temps Atomic. Somebody French, please. Atomic International. And so that one got an entirely French acronym. UTC, it's not actually an acronym. A lot of people think it's Universal Time Coordinated or something. It's not. It was actually a compromise between the English acronym and the French acronym. I'm still trying to trace this, but I think this is the last time the French got their way with naming an international acronym. Like, it basically defines the end of the European, multi-language thing, and the migration to basically everything now is defined in English. I'm not 100% sure like that. So technically, UTC does not equal GMT. But it's an alias now back to GMT. So if you go LS, it's, I'm actually pointing to UTC, because GMT was all about the solar time in Greenwich. It was not about keeping track of seconds quite specifically. So UTC is the atomic time adjusted to kind of keep time with the Greenwich time in Greenwich, which is now UT1 rather than GMT. And that's when your leap seconds come in. And we'll get to leap seconds later on. What about Python? Finally got a Python picture in here. This is a Woma python or a sand python. It's from Central Australia. It's somewhat endangered. They're very interesting. But really, what about Python? What happens when we do date time now, and get out the time of now? Well, between Python 2.7 and Python 3, there's actually been a massive rewrite of this stuff in there. And so now the class that actually deals with that is mostly Python with a bit of C. It used to be this whole module was essentially just C. And so we get the time for T there, and that is essentially a time since the Unix epoch, January 1, 1970, which for the first couple of years of January was actually set at the epoch from in the United States, from whichever lab, Bell Lab in, forgotten where it is now, and then was switched to be in essentially UTC. And then we convert this time from a timestamp in some Python class and actually convert it into a Unix, a date time class that actually knows how many hours, minutes, seconds, days, and all that kind of stuff. Internally, on Unix systems, we call this pi get time of day, which returns this pi time of day, and it in turn calls clock get time, clock real time. And clock real time has a resolution of nanoseconds. Python date time only does microseconds, and that's because we used to use, I presume it is, I'm not 100% sure on this, we used to use get time of day. On modern Linux systems, there's 3 different ways of getting the time effectively. There's the old-fashioned time, which returns a time t object, which is essentially just seconds. There's get time of day, which is not necessarily as accurate, but it was introduced next. And then this clock get time, which can get a resolution of nanoseconds, but also will tell you what resolution it thinks it actually is at. So generally it won't actually be precise to nanoseconds, but it'll say, oh, I'm pretty confident about milliseconds, microseconds. There's actually in Python 3.6 clock get time is now exposed through the Python interface, and you can get different type of clocks. So there's clock real time, which is essentially the wall clock going along, and there's other clocks, clock monotonic, which is quite interesting, and it basically means that it is always guaranteed to go forwards in time and is not linked to the actual wall clock. So it's not linked to whether or not it's now, 10 o'clock. It's just simply from when the computer booted, I'm just going to keep going forwards. So if you do have a reason to actually have your time be correctly relative to each other, that's the way to do it. The interesting thing about time and get time of day is that get time of day, it now uses, in modern Linux, uses clock get time, so they're effectively the same resolution. But time still uses a separate older way of updating it, which means if you had an application, like I did at work, which used time in some C code and get time of day in some Python code, and you run it in really tight test loops, and lop off the milliseconds, they actually don't match up all the time. There's usually about half a second. There can be up to a half a second difference between them because time doesn't need to be as fast, so Linux doesn't bother updating that particular part of your memory to tell you. So that provided a great little bit of debugging to try and work out what was going on there. So, what about Windows? Windows uses and in the Python code we use get system time as file time. This all actually happens in user space. The previous one was using a kernel call to get time of day. This actually happens in user space, so it's actually really, really fast. It just essentially just copying a little bit of memory and away you go. And it's updated, and therefore it's updated regularly internally by Windows, and it has about half a millisecond resolution. So it actually isn't as accurate as your as your Linux time. I'm fairly sure that the Mac OS is exactly the same, but I don't own a Mac and didn't get around to borrowing one to hit it with a few probes to work out what it was doing. So these things are basically asking the different ways of asking the computer what is the time in UTC so that I can go and do stuff to it. So how does a computer know UTC? It actually technically doesn't know UTC because, like all really great international standards, UTC is strictly defined as this time that all the atomic clocks plus the leap seconds, and you only really know when the atomic clocks are accurate after all the atomic clocks have sent each other files and produced a drift file. So you actually go on the internet and get the drift file, and every month they say how much is actually out by, and at that moment you can retrospectively know what your time was at a previous time. So if you are in the unfortunate case of really needing high precision time for some crazy thing, your computer won't actually give you really crazy precision UTC. It kind of just gives you a cached version of UTC. And as we know, there's only two hard problems in computer science: naming things, cache invalidations, and off-by-one errors. So basically there's a thing called NTP, which is essentially the way computers keep time, network time protocol. Windows computers have it. If you're on a local domain, you probably, at work, your computer probably just speaks a different thing to the local domain. I actually don't know much about that, and gets the time from the domain pretty much just as a, here's the time, here's the time. But NTP basically talks to other computers and says, oh, what do you think the time is? Oh, well, I think it's this time. And they all kind of sync and get the time. You can put a GPS on your network and use the GPS will eventually just work out and start spitting out UTC. And so then you can have computers. So if your time's important on your network, you'll end up having some computers talking to the outside world, getting NTP, and a local GPS. That, of course, is not without problems. So because NTP is constantly adjusting your time to make sure you're keeping in track, your time, your real-time clock, can and does change in, I put the word random in there, but it's not really random. It's kind of arbitrary ways. So it can go forward and can go back. So your computer can actually have discontinuities in time. So let's have a look at some discontinuities in time. I'm actually going to start with one of the easiest discontinuities, which is time zones. Now, most people here probably are very comfortable with time zones, but I have met developers around the world who don't understand them. So we're basically trying to keep each bit of the world having its concept that local solar time at midday means the sun's up there, it's all great. And that's essentially what time zones are about. Except India and China just basically said, we want one time zone across our whole country, and it's going to be that. And so the people in Western China essentially don't really follow the time zone when it comes to doing unofficial stuff, because otherwise they have to wait another 3 hours before getting up in the morning. They just live their lives, and when they have to talk to the government, they use the time zone. And the governments actually make these things up. They can just change them at any time. I had a friend who was flying through from Brazil through Peru to Australia, and he arrived in Peru, and Peru had decided with a week's notice to extend its daylight savings by 2 weeks. And so none of the computer systems, phones or anything managed to get the updates. Well, not none of them, because that would have been okay. Some of them managed to get the updates and some of them didn't. So you're suddenly in an international airport with a young kid, you're tired, and time is an illusion. You've got no idea. Now, a mistake I've seen some people make is assume that all time zones are integer offsets. Sometimes people assume time zones are half-hour offsets and go and implement their own sort of thing. Most of them are only half-hour or hour around the world. But there are some in what is called the Olsen database, although it's now maintained by IANA, that are actually in like 36 minutes and stuff. So, and in Olsen, the Ceduna time zone is still in there, but it's not actually kind of an official time zone in a sense. It's just Ceduna in South Australia kind of operates or did operate on that time. So Olsen was essentially maintained this database for many, many years, and essentially he did it mostly himself, and he also was the BDFL, which effectively meant, as you might have all noticed, Australian time zone codes were on Linux computers were AST and ADT, and a couple of years ago you could get AEST and ADST. So we got the A added in front of it, which was always our name, and essentially that was when Olsen lost control. People were able to get that change made. So in a sense, there's the kind of time zones are very important, but the actual infrastructure for keeping track of them globally is a lot more flaky than it kind of makes out. So if you're working on international stuff and you've got some stuff that goes into somewhere, you think, oh, well, I know the time zones, they're all really easy around the world. Well, sometimes they can just change arbitrarily, and you've got to keep up and keep on them. Also, the French have 14 time zones across the countries that they control. So what is the time in France? Daylight savings, we all know about that. It's when local time leaps forward or leaps back. This is actually a discontinuity in Windows. Pretty much all Windows computers, the real-time clock inside them isn't ticking at UTC, it's actually ticking in local time, which means when you boot up into the BIOS, which most Windows users don't do now, the time is the local wall clock, which is kind of handy. Except if you shut down the computer and bring it up again, it's got to actually do that leap for daylight savings at that time. And anybody, and I'd imagine there's probably plenty of people here who dual booted a computer so you could play games or do some Windowy stuff. And some nods. And Linux on the other one would know that your computer would, you'd boot back into Windows and go, oh, I haven't done it. And suddenly your computer would leap to 2 hours off. Mongrel. You can solve that now because there is a hack which you have to put in the registry to make your Windows computer run at real time. So just Google for real-time clock on Windows, and that'll make the real-time clock internally run at UTC, which means it can handle time zones, daylight savings transitions, and that sort of stuff. And so you get 23 and 25-hour days. In Python 3.6, we've got this extra little thing created, which is a fold flag, and so if you ask for a date time, it can actually return this flag, which will tell you that the local time you've asked for, it's actually the second time today you've experienced that time. It doesn't work when you're drunk. I tried it. But basically it means that during the daylight savings transition, the second time you ask for that time and it's suddenly 2:30 in the morning again, you can actually tell that from your local times. That's kind of handy. So the big nasty one is leap seconds. And these can be added or removed. They haven't ever been removed. Whenever UT1, i.e. the sun, and UTC differ by more than 0.7 seconds. And so since they were introduced, when they were introduced in 1972, we actually had 10 seconds added straight away. And then we've had 27 seconds. Yeah, it must not have mattered back in 1972 because I haven't heard any stories about, well, back in 1972 we had a leap 10 seconds. But now we've got these leaping 1 seconds and everybody complains about them. Now, why do we have leap seconds? We have leap seconds because the Earth and the moon are spinning around each other, and the moon is slowing down the Earth slightly. We also have earthquakes, and the big Boxing Day tsunami from 2005, 2006, 7, some year. It actually added 0.5, the change, but the difference from that one incident was 0.5 of a second between UT1 and UTC on that time alone. So we basically needed to add a leap second pretty much straight away. Now, it's all a mess. No mainstream operating system actually deals with leap seconds. They're essentially just a discontinuity and a leap in time. You can't actually find out through any standard method on a computer saying how many leap seconds there are and is there a leap second. So if you actually care how many seconds there are between 3 years ago and now, in exactly the number of seconds, and you ask your computer, it'll tell you that a number of seconds that won't include the leap seconds in that time frame. Now, for almost all applications, that doesn't matter, which is why that bug has never been fixed. And the thing is, NTP knows about it, because it kind of needs to, but it doesn't sort of just casually go, oh, we're just going to go for this second. Because it needs to convert to Unix time, which is this time without leap seconds, it pretty much just tells everybody the time has changed. And the computers try and rush towards that new second as quickly as they can get themselves in sync. Which means if you've got processes running over that need second precisions or anything, you can just get a complete mess. Excuse me. Google took the NTP code and modified it, and now they put the second in over that, sort of over a 24-hour period around the leap second. They sort of skew the time, just gently smooth it in. Okay, that's good, but if you have a computer and you've pointed one of your NTP servers to a Google one of them to something else, you're going to get mixed signals. And NTP can deal with mixed signals if it gets, basically, if it gets most of them in agreement. So if you've got 3 NTP servers you're hooked up to, 2 say this is the time and 1 says this is the other time, it ignores the one that says it's the wrong time. But if you've only got 2 hooked up, because one of them has fallen over, computers actually start ignoring that and start drifting. And virtual machines like to drift quite quickly. There was a problem at my work once where they had some NTP outages. I think maybe the internet NTP was not working, and one of the GPSs they brought in didn't deal with leap seconds properly, and suddenly, after a firmware upgrade, suddenly decided to insert a future leap second right now. This meant that some of the desktop computers all added the leap second, and a bunch of the virtual machines just stopped updating their time. So they just started wandering off randomly in time. So there are other discontinuities. There's a bug in Lotus Notes that decided that 1900 was not a leap year. Oh, sorry, was a leap year when it wasn't a leap year. They didn't do the and has to divide by 400. That has made it, for a period of time, made its way into Excel, and then also made its way, famously by Joel on software, into VBA. So if you go back to that period, you actually, have you read that article and remembered that one? Yes. So that one's a quite interesting one. As you can see, there's also some information there about calendar adoptions. I've had no real reason to go back in time and look at these things, but if you're working in genealogy and you're trying to work out, how old somebody lived for or how many generations of stuff, there's all these discontinuities around the world when dates are recorded and times are recorded and whether or not you're Catholic or not. So yes, so let's just quickly go to printing dates, and there's an XKCD. There's only one way you should print dates. Use the ISO 8601, print them out year, dash, month, dot, 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 dot. Most people not in the United States seem to get that. Most people in the United States also get that, but we've worked with people who don't. I've just realised I'm running a little slow, so I'm going to speed up. Now, parsing dates, this is actually a real problem. It's actually missing from the standard library. There's no way to take an ISO 8001 and actually parse it. Like, I don't necessarily want it to be able to parse all sorts of weird date formats, but just being able to parse a sensible one, I think, should be in there. If you do it, you can do it by specifying in here, we specify a lovely format string. A quick thing to note, this is in Python 3.6, that's formatting plus 10, plus 1,000. This one, in here, we've got a colon in there. So when it's printed out, it can't actually parse the code as it stood when I git cloned. Couldn't handle the colon in the parser. Anyway, the world is getting better. And that's not to mention other standard date formats, like if you just take date on a Unix machine. So let's just quickly go through. Hey, cheese shop to the rescue. So I went through a quick bunch of these things and determined whether or not they could parse different sorts of dates. So the pretty much standard one, pretty much any of them could parse. Some of them didn't necessarily return a Python date time object. They had their own object, which you had to convert to date time. Everybody but Arrow managed to convert the one with GMT in it, I think by ignoring the GMT, and this managed to get the date correct. And they also managed to deal with the one with the AEST, which is my time zone. But none of them seem to deal with these other time zones, even though they are valid time zone things. So I didn't actually delve down into why a number of them were actually parsing that correctly, but they didn't pick up the time zone out of there. So, 1, 2, 3, there's some flags in those top ones which will basically say, is the date first, is the time first? If you have to do more than that, you may as well just specify a format string to save you the effort. Pendulum only had one answer, and Arrow put in a stack trace which was about 2 pages telling me why it couldn't work out the date. Yeah, good stuff. So you should test against time. You should mock or freeze the time to do your tests, or mock and set an offset which offsets to a time but then continues on from that time. There's a couple of examples, freeze frogs and freeze ray, where you basically put it in your tests, and your test will be in that time. You'll ask for your date times, and they'll actually return those times. And these are particularly useful when you need to test. So you should test for 23 and 25-hour days. So if you've got something that is basically going, oh, how many hours are there in this day? I'm going to allocate some certain things, maybe work out how many hours there are that I'm going to forecast something for. You need to take into account 23, 25-hour days. You also need to test over the transition to daylight savings. If you're going to do some local time stuff, you need to do with that. And if you're really precisions, you need to deal with, if you get down to precisions, you need to basically have some code that tests around local time, just moving around with NTP and various things like that. So I'd just like to share with you this particular picture that a senior person at the Bureau noticed. She was catching a flight. Let's just zoom in on the important bit. It's a digital clock. Like, it's entirely on a computer screen, and the analog clock. How is that even possible? So clearly, time is an illusion, and lunchtime is doubly so. So, thank you very much.
Thank you. There's probably just enough to squeeze in one question, if anyone's got one. Yes, great.
So what time is it?
It's lunchtime. It's 12:34 p.m. Pretty much, approximately.
Thank you very much for an entertaining and insightful talk.
Thank you very much.